Okay, so welcome everybody to this new DaSCI seminar. Today's speaker is Professor Paolo Giudici, who is going to talk about sustainable, accurate, fair, and trustworthy artificial intelligence. He is Professor of Statistics at the University of Pavia and Professor of Machine Learning at the European University Institute. The research activity of Professor Giudici has been developed at the interplay between the academia and the financial industry. He is the author of more than 200 scientific publications, and his main research lines include statistical learning in business and industry and explainable machine learning in economics and finance. I want to thank again Professor Giudici for very kindly accepting our invitation, and whenever you are ready, the floor is all yours.
Thank you, Pablo. Thank you very much to all of you for attending. I hope, I will raise your expectations, because this is indeed, I think, a very important research area in which we put forward some contributions, but it would be very interesting to share opinions and ideas, as I believe that this is a very hot topic that deserve much more attention than it has done so far. So thank you very much for the invitation. It's a pleasure to be with you. I was in Granada a few months ago, and it's a pleasure to come back again, although virtually, but it's a very important occasion. So as you can see from the title, and also just Professor Meger just said, the talk is about essentially developing statistical metrics to, let's say, teach AI, if I can say that, to become safe or trustworthy. That is the idea, to develop metrics that can be used by AI to become safer in the sense of humans, if you want. So the whole idea is to develop these metrics to help AI to improve along our ethical lines, as written in some of the regulations that are around the world, but also according to recommendations and codes of practice. So we start from, well, the very broad definition of AI that we find in regulation that, in fact, emphasize that this talk indeed, covers also the legal definition, because it is important to match also the legal definition when we define metrics, because the metrics hopefully should be used by policymakers, regulators, and decision makers that will decide whether certain AI applications are compliant or not, like, for example, the European AI Office. So we start from the legal definition of AI in the European AI Act. It recalls definition from the OECD, in which essentially an AI system essentially transform inputs into output in a way, however, that can affect the environment. And that is underlined in blue here as a motivation of our talk. The idea that AI not only can produce accurate predictions and so forth, so it is good and or personalized suggestions and recommendations, but it can also affect the environment, whether it be physical or digital, as we know. So in that sense, it should be somehow, I don't want to say regulated directly, but it should be somehow driven towards good intentions. So that is the idea of measuring the risks, that AI measures its own risks to become safer. So this explains in more detail that the AI has, in the applications, has many advantages: efficiency, improving experience, also inclusion, because now AI can be used by many more people than expert system could in the past, no? So it can also increase inclusion. But of course, it can also increase risks, where by risks, I mean that AI can create harms for the users or for individuals and organizations, or even the environment at large. Those risks include cyber risk, particularly, that is one of the most important. Model risk, risk that the model is inaccurate. For example, in generative AI can create hallucinations, misbehaviors, and so on. Governance risk, the idea risk that AI, what is produced by the AI is not understood, and not understood in its drivers, not explainable, and therefore cannot be used to improve. Or discrimination risk, that the application favors one group of people versus the other, although the basic values are the same. So those are the 4 of the most important risks that are brought by AI, and for this reason, around the world, there are regulations or recommendations. In Europe, we have regulation that describe, brings examples of activities that are prohibited as they have a risk that is too high, activities that have high risk, like credit scoring or life insurance pricing. Those are allowed, but they need metrics to have a risk management system, like in quality control. And there are practices that are authorized, although they have some transparency requirements. So the regulation or the recommendations in the US, for example, there is no regulation, but the recommendations, they exist, and they are usually risk-based. So here are more specific examples. Here is an example about cyber risk. Here, we provide, this is a portfolio, financial portfolio. There are 5 assets, including in particular Bitcoin price. And so this portfolio essentially tells that the price of Bitcoin can be predicted depending on 5 main assets: the price of gold, the price of oil, Standard & Poor's, and so the 5 colored lines that you see there. The graph is telling you that as the sample size changes, in the beginning we have observations that are close to the mean, in the end observations that are far. So as the sample size change, the beta, the impact, regression coefficients of each variable change a lot. This means that if you have a cyber attack that alters the value of one of those 5 variables, you can have a very different prediction of the Bitcoin and a very different portfolio. So cyber risk affect the output of AI in a very substantial manner for this type of model. Here is another example about explainability. This tells you, again, for the previous problem, that depending on the model, here we have 3 recurrent neural networks, LSTM, GRU, and NAR. For each of them, we calculate Shapley values, or Shapley-Lorentz, which is a normalized version. The different predictors on the right have different explanations depending on the model. So in this case, there is a problem of governance, because if we use a GRU model, for example, that performs usually very well, the explanations are low. And so the user, they are low because most of the variation in the Bitcoin price come from speculation, not from relationship with these 5 variables. So this means that we cannot, let's say, we cannot make predictions. I mean, we don't know where the prediction comes from. We get the predictions, but we don't know what are the drivers. Is it because gold price is increasing? Is it because the dollar is improving, we don't know, because these variables they're not explainable. Whereas in the classic feed-forward neural network, the NNR, that is more explainable, tell us that the exchange rate dollar-euro explain 12% of the accuracy of the model. So that at least tell us that we can predict Bitcoin price with some degree of confidence, just taking the exchange rate dollar-euro. Here is another example. In this case, we use GPT-4, and here we use essentially prompts to, let's say, we ask GPT, we give GPT description of a borrower, someone that wants a loan. No? We tell GPT there is a person who has this income. It is a male, it has this age. Please tell me what is the credit scoring, the probability that this person doesn't pay back. So GPT has a very low accuracy, only, as you can see in red, repeating the experiment for 80 test points and with no examples, just GPT pre-trained, give an accuracy of 61%. Logistic regression, by using 30,000 data points, give much more accuracy, 75, but with a higher cost, because you need 30,000 examples. If we train GPT with few examples, like 80 only, we already get, it is called informed GPT, mean that in the prompt, for these 80 examples, we also tell GPT what is the true label. With that, we improve accuracy, and this is an example of how we can improve the performance of a pre-trained model with our data in a hybrid model. But that is clearly about model risk, because we cannot really trust a GPT model with 61% accuracy, and not even with 66. So there is a risk that our predictions are not accurate. Last, the discrimination risk. This is an example of loans, so credits actually given in the United States, in the state of New York. There are 15,000 loans for mortgages. To the right, we see the distribution is the Lorenz curve, which will also have an important role in the talk. So I go slowly to describe, if you don't recall this method. Here we have in the graph to the left, we have the loan to income. No? So for each person, individual, we measure the amount of loan they ask, I don't know, 1,000 euro, over the income they have, annual income. So the higher the ratio, the worse, because it means that that loan is not sustainable. No? So we can order this loan to income from the lowest to the highest, calculate the cumulative distribution. That is the so-called Lorenz curve to the left. We compare here the curve for white people versus curve for African American people. We see that two curves are very similar in the left. Okay, which means that the loan to income ratio is distributed similarly for black and white people. But if we go to the right, that is the actual loan received by the bank, no? Not what they ask, but what they receive from the banks. And there you can see that there is a clear difference, because the non-white people, African American, it is the blue curve. You can see that it is closer to the bisector, which means that in the beginning, there is a higher percentage of people, the curve, apart from the very beginning, otherwise it is always above the orange curve, which means that more people are given less loan among the African American people. So this is telling you that there is discrimination because the two curves are distant. We can measure the difference calculating the area between the curve and the bisector line. It is related to the Gini coefficient, or also similar to area under the curve, AUC. So the higher the Gini, the higher the concentration. Okay, so apparently the people are similar because loan to income is the same, distribution of loan to income is the same, no? But the given loan is different. So there is a potential issue of bias here that we measure with this curve. So these are examples of risks or possible harms that derive from AI. How to measure those risks is the topic of my talk. These 4 risks are also the most important risks in the AI Act, European AI Act. The first risk is called cybersecurity and robustness, Article 15. We call it sustainability because that way it covers the idea of resilience of the model, also against environmental issues. The accuracy is about model risk. The fairness is Article 10, is about discrimination. The explainability is about human oversight. The fact that the AI should actually should be understood and therefore, made contestable or monitored by different type of people, like the providers themselves or even the users that can do maybe class action. Okay, so these are the 4 key compliance principles in the AI Act. Of course, there are others like bookkeeping, data privacy, many others, but those maybe are more difficult to measure, or maybe they can be subject to auditing, or they can be included into this list in the next time. For the time being, we measure these 4 because they are measurable in continuous time. And they make altogether, they make this idea of a safe AI system where safe stands for sustainable, accurate, fair, and explainable. So our idea, this is the safe AI framework. Now we need metrics to measure whether these 4 characteristics are owned by an AI system in a concrete application or not. Lack of compliance can be translated into the probability that AI create a harm. So we need a consistent way to measure these metrics, possibly a unified way. We have one proposal, but also, of course, others can be attempted. Our idea is to use the idea of, let's say, discriminative power, but in the statistical sense, not in the fairness sense. The idea of the area under the curve. Have a metric that are good in selecting, dividing, let's say, the good from the bad. Okay, so it's not a calibration like what you do with mean square error, typically. But it's more about classification. That is, however, extended also to continuous variables, using the key idea of the Lorentz curve that I just described you in the example. Okay. So here there is an example of harm types that are the final consequence of the AI, of the lack of sustainability, accuracy, fairness, and explainability. These are taxonomy of harms due to the AI, but I don't want to go into detail, but there's a taxonomy that you can reconduct to the 4 main causes, SAFE. So how to measure those metrics in a unified way? In a way that we can get probabilities of harm. The idea is to define Lorentz curve and dual curve. So the Lorentz is what I showed you before for the loans. Lorentz curve is the cumulative distribution of the actual values. Now, suppose we have y are the values to be predicted, and y hat, y are the true observations in the test set, suppose, and y hat are the predictions. So idea is to build the cumulative distribution of the true values, is the Lorentz curve. The dual is the same curve but with the ranks reversed. So what is big, what is the largest become the smallest, and the other way around. That coincides with the worst possible prediction that you predict, you completely swap the ranks. The area between the two curves, so here in this figure, you have Lorentz curve is the red, the cumulative of the actual values of y. Suppose y is what you want to predict, what income, even 0, 1 variable, whatever. The red is the dual, so the curve but ordered in the opposite sense, from highest to lowest. The area between the two is the Gini coefficient, Lorentz zonoid. Okay. Below, you have a property that is valid for linear models, that is the Lorentz zonoid, the curves of the predictions, y hat star, are always included in the curves of the actual values. That give you a kind of R squared. If you divide the area in blue, between the blue, over the area between the red. It is like a kind of R squared, but based on the whole distribution. So this idea of the Lorentz curve can be extended to obtain SAFE matrix. Let's start with accuracy. For accuracy, with a colleague, Moera Fenetti, we developed a paper in which we propose this rank graduation accuracy, which essentially extend the AUC, area under the curve, to response variables that are not only binary, like AUC, but also ordinal or even continuous. How we do so? We do so introducing a concordance curve. What is the concordance curve? It is the cumulative distribution of the true values, but calculated in the ranks of the predictions. Okay, so suppose the true values are 10 and 20. So the rank will be that the first observation is 1 and second is 2, but maybe the prediction tell you 15 and 8. So the ranks are opposite. Okay, so we cumulate in the ranks of the prediction. So that is the so-called concordance curve. If the ranks of the predictions are the same as the true ranks, the red coincides with orange. If the ranks of the predictions are very wrong, far from the true, the concordance come close to the dual. So we can calculate the ratio between areas, like, a good model has a concordance that overlaps with orange. So it will have an area, a ratio between total area and area between red and green equal to 1. Because if the ratio between this area, green minus red, over the whole zonoid, green minus orange, this ratio, if it is 1, it means that the concordance coincides with the orange. If it is close to 0, it means that the red coincides with, gets close to green. So this way, we develop a measure. It's called RGA. This measure is just a ratio of curves, like our rock. It can be demonstrated that when the response is binary, this RGA is exactly equal to the area under the curve to use for classification problems. But you can calculate it in the same way using concordance for all types of variables. So for if you have ordinal variables, no, like I don't know, rating A, B, C, D, E, F, or continuous variables, you can also calculate this measure. Is a number between 0 and 1, the higher the better. So you can relate this to a probability of a harm due to accuracy. High value of the metric means that the probability of harm is close to 0. Here is an example, but that shows, but I don't want to go into detail, but the example essentially tells you that we can compare not only the performance of different models for one variable, one type of variable like continuous, but we can also compare models for binary response versus models for a continuous response. And we can compare, we can tell whether a certain model is best suited for continuous response, in this case was the salary of these people, or for binary response, like whether the salaries double. So that is something that was not available in the past to do this type of comparison. So that was for accuracy. For explainability, the classic tool, model agnostic tool, is Shapley values. We know about it. Clearly, Shapley value measure the change in the value of the predictions. It is not normalized, Shapley value. What we did 3 years ago is to extend the Shapley to Shapley-Lorentz. Shapley-Lorentz essentially is the same formula of Shapley, but replacing difference in predictions with difference in AUC, Lorentz zoonoid. So we get a number between 0 and 1, but we do not avoid the computational challenges of complexity of Shapley, but we get a normalized value. So in this simple example, shows that Shapley values are numbers that are difficult to interpret, whereas Lorentz zoonoid tell you the percentage of accuracy due to each variable. No? So like here we see that Standard & Poor has a global Shapley of 4 million. We don't know what it means. We just know that 4 million is bigger than 96,000. But here instead, we are saying that Standard & Poor 500 explain 30% of predictive accuracy, 33% of predictive accuracy, whereas gold, price of gold, explain only 9. So that is something more clear. It's a normalized Shapley value, but this Shapley-Lorentz is good for interpretation, but still has the computational issues of Shapley values. In this graph, it is a recent work that we are doing with a postdoc, a new postdoc that we have here. These compare different models in terms of explanations. This is a problem about phishing detection. Now we have many variables that concern the website. We have a legitimate and bad websites. And in the x-axis, we have many possible types of description of the website, like the number of hyphenations, number of exclamation marks, and so on. We have different models here: logistic regression, random forest, SVM. The explanations calculated from feature importance in random forest, they are different. You know, for logistic regression, they are coefficients. Random forest, feature importance. SVM, we use permutation plots. They're all different. So here comes the question that was very well written in a paper of Paco, the manifesto about explainable AI. No? It was a paper of that kind. It was clearly written that we don't know which explanation is better because the explanations are not robust. No? So we need a metric that tells us which explanation is better, no? So our idea here again is to use concentration. So the best explanation, of course, one can say the best explanation is the one that is more consistent with the subject matter, no? Domain field. But agnostically, we can also say that the best explanation is the most parsimonious. If you are able to do, like in this case, explain the fishing with only 2 variables, like a random forest in the middle, it is certainly better than explaining fishing with 10 variables, like logistic regression. It seems to me, because it is more parsimonious, easier to control and monitor. But that is research in progress to understand which explanation is better. Then we have fairness. So I showed you, for accuracy, we have a measure between 0 and 1, RGA. For explainability, a number sharply Lorentz between 0 and 1. For fairness, we can do a similar job. We can calculate, for example, like in this stylized figure, we can calculate the Shapley value or the Shapley Lorentz values for different variables in different groups, like male, female, or different countries. So if the Shapley value is the same for a certain variable, I don't know, income level, if the Shapley value of income, people that ask for a loan, is the same in France, Germany, Spain, Poland, and so on, we can say that it is similar across country, similar can go. Here we need a little bit of an ethical step, but we can say that similar means fair. No? How do we measure similarity? We can use, again, the area under the curve. This curve in blue, in red, is telling you that the Shapley values are the same. The curve in purple is telling you that, for example, one country has a much bigger Shapley value than the other, so it's not fair. So here we have an example of what I was telling you, that let's take the case of Spain. These are companies that ask for a loan. These are the important variables, the leverage of the company, so the level of debt, the profit loss of the company, the total asset, we describe the size. Just look at this. In Germany, the importance of the total asset is 60% of the 16% of the accuracy. In Spain, is only 10%. What does it mean? It means that if you are a large company, you want to go to Europe, maybe you better go to Germany because you will be treated better than Spain. If you are a company with good profit, instead, you know, that factor will be accounted more in Spain, 19%, than in Germany, 14%. So this can be, there's a difference. So then political people will tell us whether the difference is fair or not fair. But we have a measure that is telling us that there is a difference between the countries. So all these measures, now recently we have improved further all these measures into a unified calculation that uses concordance curve. It's called rank graduation box. For this, we also have a Python code that we developed. We generalized the previous idea of the concordance curve. So we have a metric that is called rank graduation accuracy. Measure the errors between the curves for accuracy. Another one for robustness, comparing the predicted values versus the predicted values under perturbation of the input. Same for explainability, we compare predicted value versus predicted value without one variable, RGE. Same for fairness. All of this is included in a package that we that really is free for use that include all of those measures. There are some examples. For accuracy, we calculate this specific problem of the salary doubling or growth of salary in a company, in a bank that I told you before. There are accuracy measures, in this case 0.68, 0.85 in robustness. So there are scores. Each model receives a score in accuracy, 68%. If you want, the probability of a risk, of a harm, is 32. It is quite robust, 85% robustness, with respect to perturbations that are defined by the user. Explainability is here, so we can calculate, we can sum the explainability, for example, of the first two variables, and we get a measure for explainability. For fairness, we get 93%. And so we can put all the metrics together, like in this example, in one single output. So here we are comparing, now we go back to Bitcoin prices. So during the talk, I used both Bitcoin price example and lending. They are different. One is a binary response, lending. The other one is continuous, but to tell you the framework is similar. Here we work with Bitcoin price. We have 5 different neural networks, some are recurrent networks like GRU and LSTM. Others are more classic feed-forward or radial basis function. We compare our matrix. Here we do not have fairness, because for Bitcoin price, fairness is more difficult to define logically, but we calculated sustainability, how robust they are, accuracy, explainability. And then we multiply together 1 minus this to get probability. It's a rough estimate of the probability of harm. We multiply, 1 minus this times 1 minus accuracy, 1 minus explainability. We get a probability. We can see that although the best model in terms of accuracy, root mean square error, classic measure, is GRU, gate recurrent unit, best in RMSE, if we extend our analysis to include not only accuracy, but also sustainability and explainability, the best model become a radial basis function. It's just an example, but it tells you that GRU and LSTM, are not explainable. The predictions are driven by past values of the Bitcoin price, which is not an explanation. It is just speculation. It's not that we are saying that the price of Bitcoin depends on gold, dollar, or so. We just say that it has its own dynamics that we are not able to explain. So as a result, LSTM and GRU have a higher probability of harm. Of course, here I didn't put weights on these 3 metrics. One can have priorities, can give higher weight on explainability, or a higher weight on accuracy, or higher weight on sustainability. I just made an example using equal weights. But the main message here is that by looking not only at accuracy, as we typically do in the literature, but including the other metrics, all consistent, because all measure using Lorentz curve, we get a different perspective on the models. So that is what I wanted to say. This whole model, this is what I told to the people in this. There's a working group on is developing the code for code of conduct for general purpose AI in Europe. I participate to this group. This is what I suggested. I don't know if they listen. I suggested that to use also in to monitor the trustworthiness of a GPI, the operation risk model that has been used in the financial sector since the 2000. That model is based on metrics like the ones we saw that are easy to understand and proportional to the impact of the application. So, and also the metrics that I told you can be used not only by the providers, no, the different OpenAI, Google, and so, or the deployers like banks or Zalando that is very active, just to give an example, in the area, not only by them, but also by the users, because they talk about metrics that are simple to understand. So hopefully, but that is a real wish that I don't know if it will come true, that doing so, AI can measure its own risks and thus become safer. But there's a lot of work to do together to reach that goal, I think. Thank you very much.
Okay, thank you very much, Paolo. So now it's time for questions. So feel free to raise your hand or write your name in the chat, and I will give you the turn to speak. Any questions from the audience about this very nice talk? Questions?
Paco?
Yeah, sure, go ahead.
Thank you very much, Paolo. Really very nice. I a question. Do you know the papers? We have a college from now. It's a Portuguese college working in the university now in Catalonia. Rovira Virgili. He's writing against sharp measures. She wrote a paper in a primera resonance journal that he's not agree with the sharp as a potential method for explainability. I don't agree with him because I think that it depends on the kind of problem, but sharp in these problems, when you check future, I think is so useful. But it was so extreme for me, his position against sharp. I know I will check I have I remember I include his paper in a presentation. I let me to look for. Do you know this paper?
No?
Let me 1 moment.
Maybe once I see, I recall the paper, but now it doesn't come to my mind.
Let me 1 moment. I remember to use the paper in EPIA. In my EPIA at the beginning of September, I was in Portugal. I'm looking for my presentation. Here. Let me to check. I remember to use. I don't remember, but I think later.
But if I may,
Was interesting for me because there are some people discussing about this kind of techniques. I am checking. I don't remember. I remember to use, but I am not sure when I did use them.
Sure. But Paco, if I may, I mean, I think this point is very important because clearly, here we need research that tell, if possible, which explainability method is better. No? Because as I showed you in a previous slide, this is a work we are doing now with Rashad Zieni, that is a postdoc that worked with me. We are comparing different explanations, Shapley, importance plots, feature importance, Lime, okay? They have pros and cons. Clearly, some are more computationally expensive than others, but in the end, we need criteria to compare them, no? To tell which is better, which is, depending, as you said, Paco, on the circumstances. If
I agree with you. The paper is a paper published in Approximate Reasoning, International Journal Approximate Reasoning this year. The author is João Marques Silva, and was a paper against Shapley values, but really, I think that it depends on the problem.
Sure.
On the other hand, I was this summer reading, and I already know a paper about Avery Lines, and now in American, in a ACM Human Interaction, Computer Interaction Conference, people is discussing about the interaction, of course, and artificial intelligence and humans. And really, the most important from this point of view, some psychologists and other people, and I agree with them, is really that the explainability must be useful for users.
Yes.
To remember the recent paper of summer, the recent paper that was published recently in the International Conference of in the 41st International Conference on Machine Learning. I was checking Biesek and Samek. They define red explainability versus blue explainability, and I agree with the proposal, because they define red explainability when we use it for to improve the development, basically useful for research. And
Yes.
Samek defines explainability when the explainability is useful for customers, for users, for society. I like this separation. I agree, but because it's fundamental to design explanations useful for users, of course, for doctors, for people in finance. What is your experience with people working in finance, non-expert in artificial intelligence, about the use of this kind of measure?
My experience is that in finance, usually, because it's a kind of, it is quantitative, but it belongs to economics. So there are no real physical explanations of the phenomenon. In finance, it's just, there are so many possible explanations that, typically the number of variables or features that are used is very large, in the hundreds. So then, what is my experience is that they like parsimony. When there are so many, what they like is that you end up with very few explanations. That is why we develop this idea of concentration. If, 80% of the explanation come from 2 variables or 3 variables, is great, because the user can memorize, these are the variables that matter. I'm a company. I know that to improve my rating, I have to decrease the debt, not variable 1, or I have to put more money into the company, for example. So they like this idea of parsimony. Few variables is a good explanation, because it's not physics or chemistry, it's a social science. So that there are no physical explanations. So there are thousands of possible variables that are correlated with each other, coming from balance sheets, or like in architecture, like in in architecture, possible explanation of a problem in a building are very many. So you want to have a parsimonious explanation, because with that you can mitigate. So that is my experience. But also some other people work on group Shapley. That I find very interesting, because instead of Shapley value of one feature, you can calculate the Shapley value of a group features, like all the features that relate to, the exterior of the buildings, other relate to interior, those are also useful. But explainability is difficult.
I think it's more difficult than robustness and even fairness, because we work, usually the expert, we work from a mathematical point of view.
Yes.
Probably in finance, you are working with economists, people that understand the mathematics. And of course, the variables are they understand more or less.
More or less, yeah.
More or less, but if we imagine other areas, health, when you
Yes,
are
sure.
working with image, Pablo is an expert in
Sure.
image, and other areas, really, I was reading some paper about the use of explainability for test. The SARP also starting the most important words, and it's so difficult to explain to people or to extract
Also,
the core explanation. But
yeah.
they are fundamental now in order to take decision in the cooperation human and intelligence system.
In fact, in health, for example, in fields like health and so, I think they also go by much more by examples rather than parameters, similarity. So, like the work that we are doing with José Daniel, no? For example, looking at similarities, similar observations, not variables. That like when there's an X-ray or attack radiotherapy, you look at similar examples, not variables. It's also a different perspective.
Always, I also agree with the prototype selection as an excellent approach for learning in some scenario, and I agree with you to have a good prototype with distance or metrics to have to learn or to observe the similarity. I think is a good approach. There are other people in the chat, Pablo.
Yeah, because us we can continue forever.
Okay.
Pablo, I think there are other people.
So, Manuel, if you want, you can ask your question.
Yeah, thanks. I just wanted to say thank you for this whole explanation. For instance, I'm more like in the qualitative side of AI explanation systems. So for me, it makes it like pretty much interesting from my point of view, since I'm not like really into safe AI metrics and so on. I just wanted to ask you some questions, like just one question. I don't know if you have any other example on using this safe AI metrics rather than the Bitcoin, to predict Bitcoin prices. Maybe you have some experience in using these safe AI metrics on other kind of measurements.
Yes.
And the second one, maybe should we have any access to the slides or any kind of paper so we can maybe delve deeper on that?
Sure. No, clearly the slides is not a problem for me to share with you, for sure. That's not a problem. There are, I hope that at the end of the slide, yeah, there are also reference paper, recent paper that I have. So you find them there. Of course, you can always ask me, but more importantly, yes, we have other examples. One example, we have examples in lending is a binary variable. We have a phishing detection. We have also, now we are working with text data, textual data. So we are working on analyzing claims from customers of a bank. So the customer writes text against a bank, for example, bank didn't treat me well in the interest rate, for example. And we have to, based on the text, we have to classify. There is a judge, that automatically, an automatic judge that classify the text, the claim as being, deserving attention or not, let's say. So in that case, we do the safe metric. This is more difficult because really we have text. So, but in that case, we can use similar ideas because for accuracy, we are fine. We can measure area under the curve. For explainability, for robustness, we think in terms of word removal or word replacement. For explainability, it's more difficult because it depends on the embeddings, because the text is embedded, Depending on the embedding, the semantic representation, we may have, there's another layer of complexity. So not just the data and the model that determine the output, but also the embedding of the text that we do. So that we haven't done yet. We are studying how different embeddings like TF-IDF or GPT-like transformer, how we can map the embedding with the original text. So it's an extra layer of difficulty for explainability, but also for fairness we can do the others. So robustness, fairness, accuracy we have calculated also for text. We are also now working with another postdoc on output from GPT using prompts to apply the CFA matrix using the prompts, changing prompts so to get the fairness, the accuracy, and the robustness. Again, for explainability is more difficult, but we're working.
Okay, thanks, Paolo.
Okay, and now we have the last question. Mohammed, please, whenever you want.
Thank you, Doctor, for the presentation. I just have one question regarding the metric that you've mentioned, the RGA metric, where you measure the areas between different machine learning algorithms. How do you compare this to more traditional metrics like coefficient of determination? And what's the advantage of using RGA over other metrics?
Sure. That is a very good question. Well, the idea is to provide, the advantage, clearly the advantages and disadvantages. The disadvantage is that you lose, essentially, the metric takes into account the values of the true output, the true values, and the ranks of the predicted of the predictions, not the values of the predictions. Okay, so that is the disadvantage. So we calculate, the measure is based on the ranks plus the value of the true values, the values of the ground truth. It doesn't measure the difference in the values predicted and actual as mean square error, for example. Okay, so we lose something there. We lose in calibration, if you want, but we gain in generality, because the RGA essentially extend the area under the curve, well known, accuracy measure used in classification, area under the curve that is, widely used in classification problem. It extends this idea in the similar fashion to ordinal or continuous variables. So we can use the same measure, RGA, for all types of responses. Okay, and also to multidimensional case. So it becomes more model agnostic, because often the response variable itself is part of the model, no? In the problem that I told you about salary, there was a problem in a bank, some people, I think the unions or someone, they say the growth of salary is not fair, no? But it depends. To measure fairness, you can measure fairness in different ways. You can look at the actual growth in the salary, continuous, or you can look at whether the salary doubles or increases, with a binary variable. So depending on the response, you have different metrics in the literature, no? If it is continuous, you have mean square error. If it is binary, AUC. How do you reconcile these two metrics? No? So with RGA, you can reconcile, you can get only one metric that the user understands with its probability. AUC is a probability, is a number between 0 and 1. Mean square error is an Euclidean distance. It has the advantages of Euclidean distance. Yeah, it's a metric, but it is not a measure between 0 and 1. You always have to compare mean square error with something else, no? To interpret. AUC is a percentage. So there are advantages and disadvantages. I don't know if
Well,
it was
well explained. Thank you, Doctor.
working.
Okay, thank you very much. So I don't know, I think we can end maybe here this DaSCI seminar, because if I'm not mistaken, there's in DaSCI another dissemination activity now. But I want to thank again Professor Giudici for his very, very nice talk, for accepting our invitation, and also to all the attendees for attending this seminar, and as well for their very interesting questions as well.
Thank you all for the very, very interesting question, but also very very punctual questions. I will send you the slides so you can share. Huh?
That will be great. Thanks a lot, Paolo. Thank you.
Be in touch. All I mean, I'm available. As I told you, I hope I show you that I'm passionate about the topic, because there's much to do for us mathematicians in a world that is dominated by lawyers.
Yeah.
We will keep in touch, and I hope we can collaborate soon and to discuss about potential collaboration. Paolo,
Yes.
thank you very much.
You're welcome.
José,
Thank you very much.
José Daniel, un abrazo.
Sí,
Bye bye.
ya nos veremos.
Okay, bye, thank you.
Bye bye.